Hey guys, so this is the second installment in my Chalk Talk series where I talk about steam engine facts and physics and stuff like that. So today we're going to talk about boiler physics and the difference between dry steam and wet steam. So it kind of gets into the weeds a little bit, but this should be everything you want to know about dry steam and wet steam and boiler physics, at least as an introduction. So the first thing, you'll notice I have two plots over here. These plots are going to be very important for the whole, I guess, video. Now, before I talk about that, I need to talk about something called specific volume. If you can see it, I think that's in frame. Yeah. So specific volume is the total volume of a substance divided by the mass, and it's essentially the volume per unit mass. And as an example, I have kind of two volumes here in squares. Now I just made 10 little dots in each one, and you can see that with the same amount of dots you can have different amounts of volume depending on how far away the dots are in relation to each other. So the volume per unit mass here is larger than the volume per unit mass here because they're the same mass, they're just separated out. So that's all little v is. It's called specific volume, and it's useful because it describes the properties of a substance without having to know its the specific properties of what you're dealing with. Right? You can analyze things in a very general sense. So with that knowledge, we move over to these plots, and let me actually move the camera so it's a little bit more zoomed in. Okay, so in thermodynamics, these kind of plots are very useful. This is called a TV plot, and this is a PV plot. So the V's are the specific volume we just talked about, and here that's temperature and that's pressure, and it's temperature and pressure of a substance that you're working with. So in this particular case, just imagine we have a little vessel that's open. It's not closed yet, and let's say there's some water in it, and we're heating it up with a little flame. That's a flame, and that's what we're dealing with right now. So if we look at the TV diagram first, what happens when temperature is low is that the state of the water is going to be in what's called a compressed liquid. It's just liquid. So that's the region here is compressed liquid. So as you increase the temperature, the specific volume increases, the water will expand. It's not that much. The slope of these lines are probably way too much, but regardless, the volume of the water will expand when you're heating it. But then it reaches a point, that's called the boiling point, as everyone knows, right here. And we're just going to look at this first curve for now, where it starts boiling. And the interesting about this state, the state right here, is that no matter how much you increase the temperature, it's always going to stay the same temperature. It could be 2,000 degrees, and it will stay the same temperature. And the reason for that is any extra energy that you're putting in to the substance, in this case water, is going into breaking the bonds of the water and turning it into steam. So none of that energy is actually transferring into what's heat, right? Into actually making the substance hotter, because what is heat? Heat is just molecules vibrating around. Well, if they're to the point where when you add more energy they fly off, obviously this is not going to change, right? So that's kind of what happens is the substance, the water, starts to boil over here, and this water will stay the same temperature. It's boiling temperature, right? So you can increase temp until you have no more liquid water left, and then you're in this region, which is called the superheated vapor. So it's getting a little cluttered, but I just added some labels. This is the compressed liquid section, this is the saturated mixture section, and this is the superheated vapor section. So, in terms of steam, when you have wet steam, you are in this region here, the saturated mixture, when you have a mixture of water and steam at the same time. That's a saturated mixture. And that's a wet steam because there's still water molecules that are liquid floating around in the gas, and it's wet. But once you have no more water molecules, now any extra heat you're putting into the system is going into actually making the gas molecules move faster. So after you run out of liquid water, extra heat just causes the temperature of the steam, of the superheated steam gas, to just go up exponentially. So that's kind of all this first curve we're looking at is at one particular pressure. So say atmospheric pressure. So now if we have another pressure, that you get this dashed line here, and that pressure is greater than pressure 1, and you can see what happens is the point at which it boils actually increases in temperature. So it was here, now it's moved up to here, and this difference is the change in the boiling point. And that kind of makes sense, because if you have a lot of pressure pushing down on something, you're kind of forcing the molecules to stay stuck together, and you need to have more energy, higher temperature, to break those molecules loose, because you're forcing everything down as you increase pressure. And also you can see that it becomes a saturated mixture at a higher temp. This whole thing moves up, and these 2 points kind of go in. And if you were to keep increasing the temperature, it would happen again. These 2 points would be like that until you reach a point at the top where they converge. And when that happens, you will go straight from liquid water to superheated gas. There's no mixture state. That's essentially the temperature relationship with regard to a constant pressure. So similarly to the TV diagram, you have the PED diagram, which is just at a constant temperature, we're changing the pressure, what happens. And let's say we have that same setup where we have a little vessel with water in it, but let's also say that vessel is in a container, big, huge container, like the size of the universe, let's say, such that if this boils, it's not going to cause excess pressure, right? And let's say we can just change, we have the ability to change the pressure in this container around the substance, right? So at a particular temperature, let's say T1, that's going to be this solid curve here. If we have a very, very high pressure, what happens is we are still, this is still the compressed liquid section. Right, so we're forcing all the molecules together, and they just can't escape. They're just in a liquid state. That's this section here. It's the same sort of thing. As the pressure, let's say we keep decreasing the pressure in this little vessel. As we decrease pressure, it's going to stay liquid, but then at some point, it has enough energy to kind of pop away, right, at a particular temperature. So we decrease pressure, and then molecules are able to free themselves, and they start boiling. It starts to boil as we decrease pressure, and then what happens is it'll eventually run out and turn into a vapor. What's important for boilers is if we increase the temperature, we get this dotted line. We can see that again. These two points come together, and the point in which the boiling point pressure actually increases. So I think it's, before we start getting more specifically into boilers, I think it's useful to connect with reality a little bit and make more sense of these things. An example of TV diagram characteristics is a pressure cooker. So what does a pressure cooker do? A pressure cooker increases the pressure of a pot of, you know, boiling water essentially. So what happens when you increase the pressure? When you look at this, well, the boiling point increases. And what does that mean? Well, we know that when you're boiling something, the temperature is staying constant. It's never going to get above its boiling temperature. So if you're cooking food in its boiling point at regular atmospheric pressure, you are cooking it at 212 degrees Fahrenheit or 100 degrees Celsius, no matter what. That's the hottest you can cook it. But if you increase the pressure, you can cook it hotter. You can make that temperature hotter, and you can make it cook faster. And that's kind of the characteristics of a pressure cooker. You increase the pressure, you increase the boiling point. You can cook food at a higher temperature. For the PV diagram, an example of that is air conditioners. So air conditioners, they use a refrigerant for their substance, and what they do is that refrigerant starts out as a gas, and pretty much in this region, on this right region, and it uses a compressor to compress it a lot until they get it over here in the compressed liquid state. So it goes from a gas to a liquid by a compressor. Then what they do is they will take this liquid and they will pass it into a radiator that is now, instead of this liquid is at very high pressure. What they'll do is they'll open a valve, vent the liquid out into regular atmospheric pressure. So this is a huge pressure drop. And what happens is, since that refrigerant boils at such a low temperature, something on the order of minus a few degrees, minus 23 degrees Celsius, I don't know, I'm throwing numbers out, but it's very cold, right? That refrigerant boils very cold. So if you go from a state, if you look at the PV, if you go from a state of high pressure to a state of very low pressure, well, what's going to happen? It's going to drop quickly, but then it's going to start boiling. And as it's boiling, it stays the same pressure, and it stays the same boiling temperature, which is extremely, extremely cold. So by virtue of dropping the pressure and releasing that refrigerant into the atmosphere, its temperature drops substantially to its boiling point, which is very cold, and then that cools down the little radiator. Because it's very cold, it's filled with this cold substance, and you just blow a fan through it to take some of that cold air that will cool down the air, and that's your air conditioner. And then after it's done boiling, it's back to a gas, and it just does the same thing. It recycles through, gets compressed, and so that's an example of PV diagram characteristics and TV. So this is kind of just connecting it with reality, making it make sense before we start talking about boilers specifically. So here we have essentially a boiler, right? In all these scenarios, it was kind of an open system where we were keeping either pressure or temperature constant and varying the other one. So now we're going to have a closed system, a boiler, right? And what happens then? If we have water in it, we start heating it up with this little flame. There's a flame here, and this water starts to boil. Well, at first, before it starts to boil, it's at atmospheric pressure. And let's say that's this point right here. That's this first line on either one, right? Now, you add heat, it starts boiling. But now the water molecules don't have anywhere to go, so what happens is the pressure starts to increase. And when that happens, you know from these two plots that the boiling point's going to start to increase, and it's going to stop boiling. It's gonna keep increasing pressure at this. If you don't turn up the heat, it will stop boiling at some point until it gets more energy to release those bonds. Alright, so now let's say you want to connect it to your steam engine, and you just for a brief moment, let's say you just let some steam come out just for a moment. Well, what's going to happen? Some of those water molecules have left, and that allows more water molecules to replace it. So this will start boiling again to replace those molecules that left. And when that happens, the temperature drops. You can store a lot of water molecules in a liquid state. So if you fill this boiler up, let's say to here, and now your vapor is up here, first of all, it takes less time to reach your equilibrium state at your working pressure because you have less volume up here to fill up with steam. The steam you take from this is wet steam. Because why is it wet steam? It's in a mixture state, as we saw from the plots. What you need to do, after you take this wet steam out, you need to put it through another heating cycle. So you'll pass it through a coil, and this is heated. Let's just put some flames in there. That is heated and separate from the boiler vessel. And what that does is that causes any liquid water molecules to turn to a pure gas, and then you have dry steam here. And this guy right here is called a superheater, and you need to have a superheater to make superheated steam. So after all that, let's sort of finally just talk about in terms of running a steam engine, what are the differences between wet steam and dry steam? Well, essentially, dry steam is better. Superheated steam is what you need to use. So when you use wet steam, one thing that happens is you get more condensate. By that I mean liquid water, right? Dry steam, on the other hand, if it's sufficiently high temperature, it will not condense on the way to the engine. It will not condense in the engine. It'll lose heat. It'll definitely lose heat, which will decrease the pressure, but it won't condense. Even after it does work on the piston, if it's hot enough, it still won't condense. And you just get more power to the engine. At the end of the day, you get more power, and it's more efficient. Now, the downside of using dry steam is it adds cost and complexity to the steam engine design. You have to have a superheater in place in the boiler, and you need to use piston valves, as we discussed in my last video, the last Chalk Talk video. You need to use piston valves instead of slide valves, it adds complexity. So when I say that superheated steam is more efficient, what exactly do I mean? Besides all the things we talked about here. Well, here, this is the Greek letter eta. This is the efficiency of a heat engine. It's essentially one means 100%. But we're subtracting away the ratio of the heat transferred from the cold side of the engine to the hot side of the engine. So if you have an engine represented in this block, you have a certain amount of heat input, QH, and a certain amount of heat output, QC. This is before it does work, this is after. And the ratio of QC to QH is what you subtract away from 1. Now with superheated steam, this ratio will always be smaller, and it's meaning that QC will not be as low compared to QH as it will with dry steam. Now why is that? Well, imagine you have, say, a wall. Here's the wall, and this can be any wall, the wall of a pipe, the wall of a steam engine. Let me move that down so you can see better. So you have this wall, and say you have superheated steam on this side. Well, if you're looking at if you were to plot the temperature profile, say this is temperature, the superheated steam will, as it gets closer to the wall, it drops off, and then the temperature also drops as it transfers through the wall, and then it will drop off there. So the amount of heat that drops as it's conducted through the wall looks kind of like this, right? Now if you have saturated steam, here this is superheated, so I'll make it look like that. Now if you have saturated steam, first of all, the wall is always going to be colder than the steam, right? So there's going to be a layer of condensate, essentially liquid water. And liquid water has a very high coefficient of heat transfer coefficient. So what happens is, let's make this a little bit thicker so you can see. Now, this heat will go down really quick because liquid water transfers heat out very efficiently or very well, and then it has to also go through the wall, and so you can see that there's two drops of heat. The liquid water sucks the heat out, which then transfers that heat to the wall better. So you don't want condensate because of this feature. And what will happen is that the end result, the steam that you're using, not only does this happen, now it has to do work on the piston, and every surface it touches does this kind of thing. And at the end of the day, the heat transfer coming out, QC, is going to be much less than it was with superheated steam because you don't have this condensate effect stealing the heat away. So that's going to be it for this video. I know, again, I kind of got a little bit into the weeds there with some of the thermodynamics, but I wanted this video to be everything you need to know about dry steam versus wet steam and boilers. I mean, obviously there's always more to know, but this is a good, like, how it works kind of thing. So thanks for sticking with me through this, and thanks for watching and giving me feedback and all that stuff. And if you have anything to add, please put it in the comments so everyone can see. And again, thanks for watching. See you guys next time.